Hey, want to see something cool? Non-Newtonian fluids are cool. So here I have one of everyone's favorite non-Newtonian fluids. If you haven't ever experienced what some people call oobleck, it's a mixture of cornstarch and water. And it's a non-Newtonian fluid in that it doesn't obey the Newtonian viscosity that we've talked about in previous lectures. So what's it? Why is this fluid non-Newtonian? Well, its viscosity is not constant depending on how much shear stress you're applying. So let's look at sort of two cases for this non-Newtonian fluid. So for this cornstarch and water, if I allow the fluid to deform slowly, for example by gently tilting the this tray that it's in, you can see the fluid kind of behaves like a liquid, right? It pools at one side, it flows very it flows. It's pretty viscous, but still a fluid nonetheless. But if I take this fluid and I try to deform it very quickly, I'm scraping this spoon across it. You can almost see that the fluid almost behaves, it almost becomes solid-like. If I allow it to deform very quickly, or if I force it to deform very quickly, it's almost cracking and skipping and sliding rather than flowing. You can almost see it crack. So what's going on there? Well, if you try to deform this material very quickly, then its viscosity gets so high that it almost effectively behaves like a solid. Let's talk about another non-Newtonian fluid. So this is the cornstarch and water. You can find no shortage of videos on the internet for how to make it and how to do it. And again, it's a sensation that I can't effectively give you over the internet. It's something you really got to make and play with for yourself. So find a recipe, make some cornstarch and water, and really experience how radical the change in viscosity of this material is depending on how quickly you try to deform it. So to summarize what was going on here, for this fluid, the faster I try to deform it, the more viscous it becomes. It turns out that this isn't the only, this is everyone's favorite non-Newtonian fluid, but it's not the only non-Newtonian fluid out there. There are other non-Newtonian fluids. For example, ketchup. And ketchup actually behaves in the opposite way. So right now, if you see, I have this blob of ketchup in this tray here, and right now the ketchup it's pretty much retaining its shape. I mean, maybe it's flowing very, very slowly, but if I apply very little shear stress to it, then it behaves almost like a solid. But if I give the plate a little jiggle, then the ketchup starts to flow. So I'm giving the plate a little jiggle, and the ketchup starts to flow. So this is a case, and if I give it the most extreme case where I actually hit it against the plate, hit it against the tray underneath it, the ketchup flows almost entirely like a liquid. So this is a case where the more shear stress I apply, the less viscous it becomes. So let's compare and contrast. I might have some materials where the more shear stress I apply, the more viscous it becomes, and other materials where the more shear stress I apply, the less viscous it becomes. And yet there are other materials, for example, like water and air, that are Newtonian, where the viscosity is actually independent of how much shear stress I apply. So as engineers, we're not always satisfied with just these qualitative descriptions of things, no matter how fun they are, but we want to actually quantitatively model these things. We want to use math, right? Math is one of our favorite tools, and we want to sort of say, hey, are there mathematical relationships that can predict these types of behaviors quantitatively? That's what separates the engineers from everyone else. So the rest of this lecture will be centered around mathematical models of non-Newtonian fluids, why engineers care about them, why engineers might use them, and some applications where we might see non-Newtonian behavior in biological or bioengineering systems. All right, so let's formalize this outline of this part of the lecture on non-Newtonian fluids. So we have non-Newtonian fluids. Most of the lecture is going to be on non-Newtonian fluids, but a good place to start would be with a recap of Newtonian fluids. And a lot of today's lecture is going to be useful if we frame it in terms of a plot of a magnitude of shear stress versus the magnitude of the shear strain rate. So this was shear stress, and this was shear strain rate. And if you recall, the shear strain rate is essentially the same as a velocity gradient. So we can kind of use these two things sort of interchangeably in this context. When we talk about non-Newtonian fluids, harkening back to the cornstarch and water mixture versus the ketchup, we'll talk about shear thickening and shear thinning fluids. And we'll talk about shear thickening and shear thinning in the context of this plot right here. We'll follow up this plot with another plot of a plot of viscosity versus magnitude of shear strain rate. So, and it contains essentially identical information to this, but it's just another way to sort of interpret the data and to kind of gain some insights into what's going on. Now, models, plots, equations, all that stuff is cool, but I think a lot of times what bioengineers are looking for, what students are looking for, is a connection, a description of, what are the physical origins? The physical origins of shear thickening and shear thinning behavior, right? Like, why is one material shear thickening and why is another shear thinning, right? Like, can we predict whether a material is going to be Newtonian shear thickening or shear thinning, right? Like, can we, if we understand the physical origins, then that might help us predict what type of behavior a material will have. And then finally, I'll wrap it up. We'll talk about generally what shear thickening and shear thinning behavior look like. But as engineers, we oftentimes like to have these relationships be quantitative. So we'll talk about three mathematical relationships, i.e., and by mathematical, I'm talking about new constitutive laws, right? We talked about a constitutive law for Newtonian fluids, but we're going to talk about sort of advanced or more elaborate or more complex. We're going to talk about three new constitutive laws, constitutive relationships that work for non-Newtonian fluids, that model certain non-Newtonian fluids well. So this is where we're headed. So let's start off with talking about non-Newtonian fluids, and we'll talk about them in the context of this plot that I'm describing here. So if you recall from previous lectures, for Newtonian fluids, the relationship between shear stress and shear strain rate was the following. So we had shear stress was equal to minus viscosity times shear strain rate, right, which was also equal to minus viscosity times d vx dy if we wanted to put it in terms of velocity gradient instead. But for this lecture, we're just going to be talking about things in terms of shear strain rate. So we had this relationship here. Because of this kind of goofy negative sign, I'm going to say let's be Sith and we'll deal with absolutes right here. So we'll do tau yx is equal to viscosity times the magnitude of the shear strain rate, right? So we'll just work in magnitudes, absolute values of these things, just so we have a positive thing and a positive thing here, right? So so if I think about Newtonian fluids and this shear stress, shear strain rate relationship, I might think about things in terms of a plot. Something like 90% of engineering students are primarily visual learners. So equations, meh. Plots, heck yeah. So let's plot shear stress versus shear strain rate. And if we notice that, if we look at it, this kind of takes the form y equals mx plus b. There's no plus b. So if you have no shear stress, then you have no shear strain rate, and vice versa. And this is a linear relationship between the two. It's a linear relationship for Newtonian fluids. So what might this look like? Well, we have this linear relationship, and in this case, this parameter eta, this viscosity, right? This is what we call the viscosity, is equal to the slope. The slope that's going to appear on plots here. And we notice the viscosity, if you recall, is a property of the fluids. So different fluids have different viscosities, i.e. different fluids are going to have different slopes. So let's sketch that out. Let's see what that looks like. Let's sketch two different fluids and see what their plots look like. So so imagine I have two plots right here. Pause and ponder. Which is more viscous? Which of these two, let's say this is one material and this is another material, which of these two materials is more viscous? All right, so hopefully you were able to kind of reason out some stuff here. And if viscosity is the slope of these curves, whichever one has the greater slope is going to be the more viscous one. So which one is more viscous, in this case, is the one with the greater slope, right? So what sort of insights can be gained from this plot? Well, the higher the slope, the more viscous the material is. And for Newtonian fluids, these are lines, and different materials will have different curves. So, and in general, if the faster you try to deform a material, right? So this is shear strain rate, i.e. how fast we deform the fluid. The faster we try to deform a fluid, the more shear stress. The more shear stress is required to accomplish that deformation, right? And that's true no matter what the slope is. It's just for some materials, you need more shear stress for a given amount of shear strain rate. Shear strain rate, right? So that's what's going on with this plot. But this simple linear relationship for Newtonian fluids doesn't always accurately describe fluid behavior, right? As we observed with the ketchup and the cornstarch water, we sometimes observe shear thickening or shear thinning behavior. So what would shear thickening and shear thinning behavior look like for this plot of shear stress versus shear strain rate? So let's sketch out what that's going to look like. So imagine I have a couple of cases here. So let's look at right here. Let's imagine this blue line is what some Newtonian material, some viscous Newtonian material would look like. So if it were, let's say, shear thickening, the faster I move it, the more viscous it appears to get, right? So, so Newtonian fluids, the more shear stress, the more shear strain rate. But shear thickening, shear thickening materials require even more shear stress. It's sort of a greater than proportional amount. As a function of shear strain rate. So, and in a sense, that cornstarch and water, above a certain shear rate, it almost required a near infinite amount of shear stress to deform it, right? It basically required so much shear stress that the material itself just cracked. And so shear thickening materials, so almost all materials, the more shear strain rate, the more shear stress. But shear thickening materials require an even extra amount compared to what their Newtonian counterparts would have been. We can contrast this to shear thinning materials, where as you increase the shear strain rate, it still requires more shear stress to move them, but less than there would have been for their Newtonian counterparts. So, almost always there's, the more shear strain rate, the more shear stress is required. So, this curve is still increasing, but just less than there would have been for a Newtonian fluid. And this is what we call shear thinning behavior. So, and we can have shear thickening and shear thinning behavior that essentially describe deviations from what the Newtonian behavior would have looked like. So one quick clarification for this plot here. Shear thickening doesn't necessarily always mean, in an absolute sense, it is more viscous than a shear thinning fluid. So for example, we could have a fluid that is shear thickening, i.e. that it sort of deviates from a non-Newtonian fluid, but it could potentially be less viscous than a shear thinning fluid that deviates down, right? So we could have shear thinning fluids that deviate downwards from a Newtonian thing, but in an absolute sense, they could still potentially be more viscous than a shear thickening non-Newtonian fluid, right? So we can have fluids that, in an absolute sense, are low viscosity, but shear thickening. And we could have fluids that are, in a sense, high viscosity but shear thinning. We could also have fluids that are low viscosity and shear thinning as well, right? So whether it's shear thickening or shear thinning describes the deviation from a linear relationship, which is the Newtonian, but in an absolute sense, you can still have very viscous shear thinning fluids or low viscosity shear thickening fluids. All right, so here we've talked about shear thickening versus shear thinning fluids. All right, so we talked about Newtonian fluids. We talked about this plot of shear stress versus shear strain rate. And we talked about how, in the context of this plot, we can observe shear thickening or shear thinning behavior. Now, let's talk about one additional plot, which is this viscosity versus shear strain rate plot. So sometimes, to analyze these non-Newtonian fluids, rather than plotting shear stress versus shear strain rate, it's sometimes useful to talk about a plot of viscosity versus shear strain rate. And let's just work in magnitudes here, right? So what would be the viscosity as a function of shear strain rate? Well, in a sense, this plot that I'm proposing to create here is sort of a description of what the slope of these curves as a function of this, right? So in a sense, this curve down here is sort of like a derivative of these curves right here. So I pose this as a challenge to you. Pause and ponder. Sketch the 6 curves in the tau yx versus shear strain rate, the shear stress versus shear strain rate plot. So take these 6 curves here and plot what their equivalent viscosity versus shear strain rate curves look like. So I'll leave this on screen. You can pause and ponder, sketch what the viscosity versus shear strain rate looks like for each of these 6 curves. So keep in mind, viscosity is essentially the slope of these. So we're essentially plotting the slopes of these curves here. So I'm going to keep the nomenclature, solid lines representing these 3 and dotted lines representing these 3, and the color coding between shear thickening versus shear thinning, and Newtonian the same, right? So if I look at this blue curve, its slope is essentially a constant over the whole shear strain rate phenomenon, right? So if I look at what the slope of this is as a function of shear strain rate, well, it's just a constant for the whole shear strain rate. So the solid blue curve looks something like this. Similarly, the dotted blue curve is also a constant as a function of shear strain rate. It's just a lower constant than the solid blue curve. So the dotted blue curve is going to look like this, also a constant. The shear thickening curve starts out at the same value. This solid shear thickening curve starts out at the same value. Starts off with the same slope as this blue one, but its slope increases as we go on. So what's that going to look like? Its viscosity starts off as the same, but increases. And for the dotted one, its slope starts off the same, but then increases. And for this the dotted black one and the solid black one, the slopes start off the same, but then decrease relative to their counterparts. Right, so for the black one, we might get something that looks like this, or like this. Right, these are mostly just qualitative at this point. Don't try to necessarily quantify exactly what's going on here. But we can basically see, sometimes it's easier to interpret these shear stress versus shear strain things to talk about viscosity and just think about slopes. Sometimes it's easier to plot what the actual slope is as a function of shear strain rate. Constants would be Newtonian. And shear thickening go up from their Newtonian counterparts, shear thinning go down from their Newtonian counterparts, and more viscous curves are up here, less viscous curves are down here. So we've now talked about this plot of viscosity versus magnitude of shear strain rate. Now let's talk about the physical origins of shear thickening and shear thinning behavior. And of course, this is going to be different for different materials. So I'm going to talk about these origins of shear thickening and shear thinning behavior for a couple of fluids that bioengineers care about. So first, let's talk about shear thinning. Shear thinning non-Newtonian fluids. I'll just abbreviate that as NF. And first, let's talk about it for ketchup, and then let's talk about it for blood, which is actually a non-Newtonian fluid as well, that things care about. So let's talk about ketchup. So ketchup essentially has this molecule. It's mostly water, has a little bit of vinegar in it, but it also has these polymer chains in it. It's essentially a suspension of polymer chains. And let's sort of look at two situations where the ketchup could be under. So let's look at the case where there's no shearing going on. And then let's look at the case where there's shearing going on. So if there's no shearing, polymer chains tend to kind of clump up into these little balls, just sort of due to the random bumping and jostling of the motions. It sort of tangles and clumps up the polymer chains a little bit. So Ketchup sort of has all these polymer chains kind of jumbled around in them. But if we take shear stress and apply it, that shear stress essentially stretches out, it pulls the top of the flow in one direction and pulls the bottom of the flow in the other direction. So what happens to each of these polymer chains if we apply enough shear stress? Well, we actually fundamentally change essentially the material itself. If you take shear stress and you stretch it out like that, each of these polymer chains are going to stretch out and untangle, right? So when we're shearing, we untangle each of these polymer chains due to the shearing motion. So what does that mean? We basically take out all of our polymer chains and we kind of stretch them out like this. Now, how does this change the viscosity of the material? Well, if you think about it, if at this case where there's no shearing, or not no shearing, but just very little, right, or very little, if there's very little shearing, each of these clumps kind of occupy some space. And if we try to move them past one another, they bump into each other. But if you imagine, once I've sheared them out, once I've stretched out those chains a little bit, they can glide past one another without bumping. Right? So if these polymer chains, once I've sheared them out, can don't bump past one another, or don't bump into each other once the shearing is going by, then if they're not bumping into one another, they're not stopping the flow. They're not stopping the the greater material around them from deforming. So if they're not bumping in, they can slide past one another. But if you let go of that shearing, the polymer chains eventually kind of contract into their original shape. So if you shear them faster, if you shear them apart faster than they can contract back together, then you get this case where it's not very viscous and they can slide past one another. Whereas if the retangling is faster than the shearing apart, then the material appears to be very viscous. And that's kind of consistent with this plot up here. You know, if I can pull these chains, if I can shear it so fast that these chains can slip past one another, then I'm in a low viscosity region over here. Whereas if I'm in a region where I allow the chains to contract and bump in and then become so big that they bump into one another, they kind of occupy these sort of spherical shapes, then they bump into one another and the material appears to be more viscous. It turns out that not just ketchup does this, but also your synovial fluid, which is all the juices that lubricate the cartilage between your joints. So it turns out that the lubricant between the cartilage and your joints is actually shear thinning. And that's actually a pretty sweet evolutionary advantage. You can imagine it's nice to have the material be viscous when my joints aren't moving. And that's so the material itself doesn't leak out of the joints. But once I start moving, I want that viscosity to go way down because, you know, I don't want there to be too much shear stress between my joints. I also don't want too much resistance to motion, right? So the shear thinning behavior of synovial fluid actually confers an evolutionary advantage in that it allows us to move around when we want to move, but it prevents the fluid from leaking out by sort of increasing its viscosity when we're choosing not to move. So shear thinning synovial fluid is pretty awesome. And actually one of the hallmarks of arthritis is a loss of the hyaluronic acid, which is the polymer that makes up these clumps in our synovial fluid. So that's shear thinning. It turns out blood is also shear thinning, but for a slightly different reason. So blood, if we kind of picture blood, a lot of what makes up our blood cells are red blood cells. And if we sort of look at a side view, they're kind of these sort of donut-shaped kind of things. But the blood cells oftentimes stack up into these sort of coin-like structures, and the blood cells sort of form these pretty weak bonds between one another, right? So if you just let the blood cells just kind of diffuse around, eventually they'll bind to one another and form these kind of stacks. They're called rouleaux. So if there's no shear stress, then the blood cells stack up to basically form these rouleaux. But if we apply shearing, then we break up these stacks. And you can imagine if these stacks form, they can eventually, build out to one another to eventually form almost solid-like networks. They can form networks. Right, and that essentially almost creates a gel-like or a solid-like structure within the blood. But if we apply shear stress, we break up all of these stacks into a bunch of freely free blood cells. So if I shear these stacks of blood cells, let's say pulling the top one way and the bottom the other way, I break up all of these, so there's no longer this solid-like structure. But you might be like, hey, wait a second, is that going to make these all bump into one another? And the answer is no, not really. The blood cells don't bump into one another too much because the cell membranes are actually sort of very loosely wrapped around sort of blobs of fluid. And the cell membranes can almost kind of tank tread, right? Have you ever seen like the tracks on like a tractor or an excavator or a tank? The track on the tank can kind of roll around the outside. So if you can imagine, all of these blood cells can kind of tank tread around to sort of slide over and not really resist the shear stress. So this tank treading behavior basically allows the blood cells to sort of slip and roll and slide past one another. And there we go. But if you then relax the shear stress and give the blood enough time to form these stacks again, then the blood sort of regains a solid-like behavior. So blood actually turns out to be shear thinning for this reason. But wait, Professor Lannin, you might say, what are the origins of shear thickening behavior, right? We talked about physical origins of shear thinning behavior. What are the origins of shear thickening? What are the origins of shear thickening behavior? Well, it turns out a lot of shear thickening behavior comes from suspensions of rigid particles. So suspensions of deformable particles could, depending on the context in this binding behavior, exhibit shear thinning behavior, but suspensions of rigid particles are actually the opposite and exhibit shear thickening behavior. All right, so shear thickening behavior oftentimes occurs in suspensions of rigid particles. So let's say we have no shearing applied. You can kind of imagine I might just have a suspension, a suspension of particles like this in water, and these could, for example, be little globules of starch, which is kind of barely soluble in water. And we could have water all around it, right? So shear thickening could be something like this. But if I apply some shear stress, I now make these particles need to sort of slide past one another. But if it's a very dense suspension of rigid particles, for example, in my cornstarch and water, I put in actually a greater amount of cornstarch than I did water into that suspension to try to make it right. So that is a very dense suspension of starch particles. And I try to shear this dense suspension past one another. All of the particles jam against one another. So all the particles basically kind of get I try to move these particles past each other, they jam into one another, and then this jammed particles then sort of exacerbates it, right? It's like a traffic jam. If one car cuts another car off, then all the cars sort of put on their brakes and slam into, and well, hopefully not crash into each other, but sort of halt motion, and you end up getting this traffic jam of particles. So the shearing motion actually presses the particles into one another and creates a kind of jammed network of particles where they've all bumped into one another, and the shear stress kind of keeps and locks them in. The shear stress locks them into this jammed structure. And then if you let go, eventually the thermal motion can kind of jiggle the particles free, and they can go back to this freely flowing state. But if there's no shearing or very little shearing, we give these particles time to slip past one another. But if we try to deform that structure too fast, the particles jam, we form this rigid network, and the rigid network can't really break apart unless you apply so much shear stress that the material itself actually cracks. But that's not really not the non-Newtonian part of it. Right? So particles jam, and we get shear thickening behavior. So Professor Lannin, all this stuff sounds great, right? Qualitatively, I'm feeling this really clicking, but I'm an engineer. I'm not satisfied with just a qualitative description of something. I want you to give me some mathematical relationships. What sort of functions could potentially describe these curves? So let's do that. So let's describe 3 functions that can model non-Newtonian behavior of fluids. So first, we'll start off with so model number 1. Model 1 is what I'll call a power law fluid. And in this case, for a power law fluid, the magnitude of shear stress is equal to a slightly different relationship. So I'll call it, it's minus capital K times the absolute value of d Vx dy to the n minus 1, or dvx dy to the n minus 1 times dvx dy. Or we could sort of lump these two things together as just minus k times dvx dy to the n, and of course you could replace dvx dy with shear strain rate if you wanted to as well. So what does this look like, right? So this is, in a sense, this isn't too different. This isn't too different from the, this isn't too different from the Newtonian relationship that we had earlier, right? We still have tau on one side of the equation. We have some constant times shear strain rate, but in this case, instead of shear strain rate, here we have shear strain rate to some power n. And instead of viscosity out front, we have this parameter called capital K. So, so there we have it, right? So take a moment now, pause and ponder. What is n for a what would be n for a Newtonian fluid? So pause, ponder, see if you can work it out. Okay, hopefully if you worked it out, pause and ponder, what would n be for a Newtonian fluid? N would be equal to 1 for Newtonian, where if we bring back this relationship here, if we take, shear strain rate to the power of 1, that's essentially n equals 1 is sort of the same as this. And in this case, K would be the same as viscosity. For a power law fluid with an n of 1, that's essentially the same as a Newtonian fluid. Now, let's sort of look at another pause and ponder question. Let's look at cases where n would be greater than 1 or n would be less than 1. So pause and ponder. What does it look like if n is greater than 1? What does it look like if n is less than 1? Pause and ponder. Consider, you know, what physically does this mean? Well, hopefully you've paused and pondered. N greater than 1 is a shear thickening fluid, right? So for example, if we wanted to sketch out what this looked like, magnitude of tau versus magnitude of shear strain rate, let's say we put an n of 2. In this case, tau would be proportional to shear strain rate squared. And shear strain rate squared looks kind of like a parabola. And that's kind of consistent with this shear thickening behavior that we talked about earlier. So shear thickening is this n greater than 1. N less than 1, well, if let's sort of, you know, for example, do, oh, sorry, so shear thickening, I want to keep my color coding consistent. I'll do red for this, all right? If we did n equals 1, then it's a straight line. N greater than 1, n equals 1. And let's just say, you know, for shear thinning, let's, for example, do n equals 1/2. Well, n equals 1/2 is kind of like y equals the square root of x, or tau equals the square root of d dx dy. So the square root looks something kind of like this. And that's n is less than 1, which is consistent with shear thinning that we talked about earlier. So power law fluids can actually describe a pretty broad range of non-Newtonian behaviors, right? We can get shear thickening versus shear thinning with this control of n, and k, of course, scales up or scales down the whole overall slope, right? So k essentially gives us control over the sort of total magnitude of the viscosity, and n essentially allows us to account for the deviation above or below of what linear would be. So k is sort of the overall viscosity, n is kind of the deviation from linearity. All right, so let's move on to another model. So sometimes, you know, power law fluids can describe a pretty broad range of non-Newtonian fluids, but they don't necessarily describe all of them. Let's look at model 2, which I'll call a bingham plastic. And an example of a fluid that behaves as a bingham plastic is toothpaste. All right, so here I have some toothpaste, and toothpaste, I can squeeze out a blob of it, and, you know, I could look at this blob here, and maybe that's a little better without the light. And I could just keep this blob of toothpaste here, and it almost behaves like a solid, right? So toothpaste is it's almost totally solid up to a point. You know, there's this piece of toothpaste, you know, it's not going anywhere. But it definitely flows like a liquid if I apply enough shear stress to it, right? So I apply some shear stress to it, it can flow, right? I squeezed it out of the tube, right? It's not totally solid. So how does this work, right? How do we qualitatively model this behavior? Well, if you imagine shear stress versus shear strain rate, for this weird toothpaste bingham plastic material, I apply more shear stress, up into a point, and then only once I reach some critical level of shear stress do I start getting flow after that. So what does this look like? Well, there are sort of two parameters that kind of define what the behavior of this material is. One behavior is this kind of slope after it, and then another behavior is how much shear stress I need to apply before I even start getting any shear strain rate at all. Right? So this point right here, this stress level right here, after which I start getting some motion at all. This is called the a yield stress, or sometimes just tau sub y. So it's like a yield stress, and then after here, this is kind of like a viscosity. This is sort of a viscosity-like term up here. And so what does this model actually look like? You can kind of you can model it this way. You can say so if we want to model this mathematically, we almost need to break it up into 3 separate regions. So we can also imagine, if I had negative shear strain rate and negative shear stress, I would almost sort of need to sort of extend this kind of symmetrically the other way. So we almost need to, it's sort of like a piecewise function. We sort of need to break this up into 3 separate regions to mathematically kind of define them separately. So we basically want to say between minus tau yield and plus tau yield, shear strain rate is going to be equal to 0. So there's kind of here's sort of one case right here. And then another case we have is if your tau is above tau yield, then tau yx is going to be equal to tau yield plus mu naught times gamma dot. And let me just get my negative signs right here. So minus tau yx would be equal to this, right? So basically, like if you're above a certain threshold, then it kind of looks like a y equals mx plus b sort of situation, and over here, right? And of course, you need to get the minus signs all worked out. And oh, sorry, I forgot a minus sign right here. We got a minus sign in there. And of course, the sort of opposite relationship would be worked here, where in this case your y-intercept would be minus b. All right, now let's talk about a third model, which is a casson fluid. So if we have a casson fluid, it turns out casson fluids are a little goofy, and the square root of the absolute value of tau yx is equal to this parameter s times the square root of the absolute value of shear strain rate plus the square root of tau yield. Or gamma dot equals 0 if the magnitude of shear stress is less than tau yield. So casson fluids, blood is an example of a casson fluid. And you know, what is this plot? You know, what is all this square roots and absolute values and all that stuff look like? Well, if you plotted square root of tau yx versus square root of gamma dot and the absolute values of these two quantities, right? If you plotted the square root of the absolute values of these two quantities, then it would look, then your plot would sort of look linear. Or it would look linear, but with this sort of like no strain rate until a certain stress, and then linear after that. But the actual relationship between tau and gamma dot is not a linear one. It's just the relationship between their square roots is linear. So anyway, before you panic, before you're like, oh my goodness, square roots and absolute values and I'm freaking out, right? Spoiler alert, we're not actually going to use caisson fluids too much we're not going to use it hardly at all, except for like one problem and one homework assignment. We're not actually going to use Bingham plastics too much. We're only going to use power laws once, and we're going to be doing the bulk of this course with Newtonian fluids. So you're like, hey, wait a second, blood and all this stuff, all these biofluids that are super awesome and super interesting, they're all non-Newtonian fluids. And I'm like, yeah, but we can really only get useful mathematical results a lot of times with Newtonian fluids. So we'll develop a lot of intuitions for fluids using Newtonian fluids. We'll oftentimes be able to make very useful approximations to flows using Newtonian fluids. But sometimes if you want to really, really simulate a system super accurately and the fluid is non-Newtonian, you need to use one of these more complicated models. So, so there we have it. So, so you might ask yourself, you know, which constitutive relationship should I use? Which one should I use? For example, like if I had data, which model might be the most appropriate? So I'd say the first step would just be to plot tau yx, its absolute value, versus the absolute value of shear strain rate, and then see, you know, if it's linear with y-intercept equals 0, then what do you have? You're going to have a Newtonian. Then you have a Newtonian fluid, and slope is going to be equal to your viscosity. If it's linear with y-intercept not equal to 0, then you have a Bingham plastic, and slope is equal to mu naught, and y-intercept is equal to yield stress, is equal to your yield stress. If it's nonlinear, things might be a little bit trickier. But so if it's nonlinear, then you have the possibility that it's either a power law fluid or a caisson fluid. But if we notice, hey, this power law fluid kind of has this relationship here, right? So if it's a nonlinear, then try taking natural log of absolute value of tau yx and plotting it versus the natural log of the absolute value of shear strain rate. And it turns out that if you take the natural log of both sides of this equation, natural logs have some cool properties where for a power law, the natural log of the absolute value of tau yx would be equal to the natural log of, I guess if we take the absolute value, then we get the right-hand side. The natural log of tau yx is going to be equal to the natural log of k times the absolute value of gamma dot to the n, right? That's just what I just plugging in here, just taking the absolute value of the side, right? I guess absolute value Sorry, I shouldn't have had this negative sign there, but absolute value would be the absolute value of this. If you take the natural log of a product, then you get the natural log of k plus the natural log of absolute value of gamma dot to the n. And if you have a power inside of a natural log, then that can come out as a multiplicative factor in front. So you can, so if you have a power law fluid and or if you have some nonlinear relationship between these things and you take natural logs, if you take natural logs and the relationship between natural logs is linear, then you get your result, right? So if you take natural logs of both sides, you can kind of treat this as your y, and you can treat this as your x, and in this case, the slope of y versus x would be the power of your power law, and the y-intercept would be the natural log of this k parameter for power law fluids. So this might be helpful in a homework problem, hint, hint. So, in summary, talked about physical origins, and we also talked about some mathematical relationships. So we have non-Newtonian fluids. We talked about, hey, Newtonian fluids, you have this linear relationship between shear stress and shear strain rate. But sometimes in real life, so we have this linear relationship between shear stress and shear strain rate, or their magnitudes anyway. We can have high viscosity or low viscosity fluids depending on the slope, and deviations from these linear things can be represented by shear, or can be used to describe shear thickening or shear thinning behavior. We also talked about how instead of plotting shear stress versus shear strain rate, we could talk about plotting the derivatives of these things, in which case you get constants for Newtonian fluids and deviations for non-Newtonian fluids. We talked about the physical origins for some of these things, i.e. untangling polymers to slide past one another, pulling apart stacks of red blood cells, or jamming traffic jams of solid particles to explain shear thinning or shear thickening behavior. And then we talked about 3 mathematical relationships for non-Newtonian fluids, that being a power law fluid, a Bingham plastic, and a casson fluid. And we wrapped it up with describing, hey, if I were given some data, you know, could I create plots of these things to try to tease out, you know, which non-Newtonian fluid the material might be. So, thanks for watching. Be sure to ask any questions on Canvas or in the YouTube comments if you have questions. And good luck with your fluid studies. Thanks.